Muito bem. Bom dia. Good morning, everyone. Today we'll have Peter Scholze from the University of Bonn, whose work is very renowned in our area, in arithmetic geometry, for having basically introduced a tremendous amount of new techniques to deal with questions related to p-adic geometry. However, what is going to present today is slightly different from his usual stuff. Rather, it concerns a tentative of setting up a formalism which deals with, let's say, topological phenomena in algebra in a way that is uniform and homogeneous. And this would have the potential application, as he has stressed in one of his lecture notes, of maybe extending the type of colonization that algebraic geometry has been undertaking for the last 50 years, to extend this now to analysis itself, more specifically functional analysis, which is, I'm not sure if he's going to talk about this, but yeah, it's certainly in the realm of possibilities right now, somewhat. Yeah, so I guess I'll pass the word to Peter Scholze right now.
All right, thanks, Joe. Yeah, it's a pleasure to speak here at this conference of the Portuguese Math Society. Yeah, so I want to talk about some kind of long-term project that I pursue, particularly with Dustin Clausen, termed Condensed Mathematics. This is something that so we're doing this summer. We started this project in the fall of 2018, and I gave some lectures in Bonn about this. And yeah, I don't know. We'll see where it leads us in the future. So what's the basic claim of condensed mathematics is that this very classical notion of topological spaces that was introduced, I think, by Felix Hausdorff about 100 years ago is actually the wrong notion. And you should rather consider something very closely related but slightly different that we termed condensed sets. And that this resolves rather large collection of foundational problems that one has when working with topological spaces. So let me first try to indicate some of the problems one might run into when one works with topological spaces. So what are topological spaces? Topological spaces, I mean, they formalize the idea of spaces with a notion of, I don't know, informally speaking, nearness of points. So it makes some sense to ask the question whether 2 points are near in a topological space. So you have convergence phenomena and so on in topological spaces. But one thing they cannot really talk about in a meaningful way, but they fail to formalize, or handle the idea of points that are infinitely near but distinct. In a useful way. So let me try to give some examples. So I mean, the one very large class of examples arises just in the following way. So you have some nice space X. So say this could just be the real line. And acting on it, you have some group G. Some nice group. And so this might be, well, maybe I want to consider two cases. So either by translation, you can have the integers acting, or you could also have the whole rational numbers acting by translation. And then you can try to form the quotient of X by the group G, the quotient space. So you identify any 2 points that lie in the same G orbit. So then in one example you get here is the quotient of R by translation by the integers, which is of course some wonderful circle S1. And well, that's a wonderfully beautiful topological space, no problems here. But when you take the quotient of R by the rational numbers, well, that is a funny space, right? Because I mean, you're basically identifying, well, not just a circle, but then you're wrapping the circle around once more and making it smaller and smaller. So I mean, you have some kind of very, very, very small circle in the end, where you like immediately return to the start when you walk a little. But I mean, it still has many different points, right? So I mean, so 0 is still not equal to pi in this quotient space because Q is pi is irrational. So there are different points in there still, but they're also all infinitely near to each other. So any neighborhood of one point will contain any other point. And so, I mean, this is indiscrete, and so it doesn't have any real, definitely, the topology doesn't see anything anymore. And I mean, you can have many, many examples of this sort. I mean, in mathematics, you have lots of cases where you have some space, maybe some hyperbolic space or whatever, and you have lots of groups acting on those, lots of symmetry groups. Now, very often you would like to pass through a quotient space, and we're somehow trained to never do that if the orbits are dense. But then we just decided that the quotient space is not something we should ever really consider. Yeah, because it's not a useful, it doesn't have any useful structure as a topological space. Okay, so that's the basic issue. Well, this also arises in functional analysis. So if you say take this space of summable sequences, you take this space of all sequences of real numbers, which are summable. This can be embedded into the square summable sequences. Oops. And then, I mean, you might also, I mean, this somehow has dense image, but it's of course not surjective. And then you might also maybe want to contemplate something like the quotient of this L2 space by this L1 space. And again, this is just some indiscrete R vector space, so that doesn't have any interesting structure. So you can't do functional analysis with such spaces usually. You try to avoid those. So that's the basic issue that you have in topological space, and somewhat traditionally we are just trained that we just shouldn't do that. But I claim that there is a formalism. You can replace topological space by condensed sets. And then you can just do these operations. And as condensed sets, these things will just be as well behaved as anything. So you don't run into any actual problems. So the claim is that when replacing the topological spaces by condensed sets, these quotients are still reasonable. Okay, let me, before I go on and say what condensed sets actually are, let me list a few other problems that one may know about topological spaces. So another kind of foundational thing is that if you've given two topological spaces, X and Y, we do not have what's called an internal HOM. So the topological space HOM XY is such that mapping any other space Z into the space continuously into this map space of continuous is the same thing as someone giving a Z-index family of maps from X to Y. So this is some kind of general categorical theoretic thing that one would like to have in the category, that if you have two objects and there's some kind of object of maps from X to Y, but this doesn't exist in topological spaces, so that's also bad. What are some other things? Yeah, so somehow if you try to mix topology and algebra, and I mean, I'm an algebraist, so I want to do algebra, but sometimes my objects just carry a topology because, I don't know, I'm doing a lot of p-adic stuff, something like this. And so I want to consider things like topological abelian groups. But these do not form an abelian category. Which is a kind of thing that algebraists like, and it's supposed to use maybe like property. It's a thing where you can do all these kind of homological algebra constructions. So they always work with these abelian categories. And topological abelian groups just are not of this form. So basically the problem is that if you say take R with its discrete topology, mapping to R with its natural topology, this map, then this is somehow injective and surjective. But not an isomorphism. Because the topology changes. But in an abelian category, a map that's injective and surjective should be an isomorphism. And so this can't be one. What else? Yeah, I don't know. I mean, you can somehow continue to do some kind of homological algebra. You can try to push it a little, but I mean, even if you then consider some kind of complex of topological abelian groups, then the homology, so the kernel of di what's the image of di plus 1, may again be such a pathological object. Like, say, such an L2 mod L1 space. So I mean, these Gaussian objects, they just occur naturally when you try to do any kinds of arguments. So if you want to somehow mix topology and algebra in a good foundational way, you need to have a formalism where you can really talk about such quotients. So, yeah. So the claim is that in condensed sets, and these problems disappear. While at the same time, you don't really create any big new problems. So yeah, so maybe at this point I should say what these condensed sets actually are. So the idea is that instead of formalizing neighborhoods, so topological spaces are somehow based on this. You try to formalize this notion of nearness in terms of the notion of neighborhoods of a point. And somehow this notion is just not suitable if you have some space like mod Q, where any 2 points are infinitely near, so there are no non-archimedean. Formalize more or less the notion of converging sequences, or more, kind of how things can converge. And so some are converging sequences. In some space X, they're exactly the continuous maps from the space 0, a half, a third. Sorry, I want to start from 1. 1, a half, third, 0, 2x. So you have this space. Okay. You have it somewhat. This thing here is somewhat like the generic convergent sequence. And yeah, if you want to consider any convergent sequence in space X, this should be the continuous maps from this kind of example space of convergent sequence into X. And this thing here is actually, well, it's a totally disconnected compact Hausdorff space, if you want. Such things are also the same thing as limits of finite sets. So if you want to think about this set, you can somehow draw finitely many points in the limit point, and then resolve this by taking more and more of these finite points here, and then taking the limit of all of those things. Then you recover this thing. So these are the same thing as profinite sets. A different way yet to think about those is there's so-called stone duality, which gives an algebraic description of what this category is. It's the same thing as Boolean algebras, or rather the opposite. It turns out that it's better to not just consider how a sequence may converge, but more generally how any kind of totally disconnected compact Hausdorff space maps into X. So one reason is that in a general space, you might not have enough convergent sequences, and so to really still see interesting structure, you need to allow larger kind of sequence spaces. So yeah, but I mean, this category of totally disconnected compact Hausdorff space is just a rather beautiful category, good properties, and so it's a somewhat reasonable idea to somehow base everything on that, and so that so the condensed set by definition should be determined by how profinite sets map into it. So the slogan is a condensed set. More prosaically, it's a functor from profinite sets to sets, and it's contravariant, so it takes any f to x of s, which should be from the continuous maps. From S and J. Satisfying some properties. I mean, one stupid thing is that if you take the value at an empty set, then, well, how many ways should there be to map an empty set into anything, well, there should be exactly one way. Also, if you map a disjoint union of things, then this should be the same thing as mapping those parts of it. And then there's one further axiom. So there are some very simple properties that this should satisfy. Okay, so that's all. That's the condensed set. And I mean, the obvious class of examples is that if you start with topological space, then what I will call T underline, which takes any S to the continuous maps from S into T, is a condensed set. And so, at least on so-called compactly generated, which is almost always satisfied, these compactly generated topological spaces, they embed, so injectively or more precisely in this category theoretic language, fully faithfully into condensed sets. Okay, so you still have all your good old topological spaces that you know and love, but you get a few more. And you get them in a way where somehow now the new bigger category somehow has much nicer properties. Right. Yeah, so let me maybe at this point remark how this actually solves some of these. So what will actually happen in these examples here? R mod Z and R mod Q. Well, if you take these quotients, then, well, I mean, the S value points of the reals, or reals underlined, are the continuous maps from S into the reals. So particularly S is the space of abstract convergent sequences, and well, this is just the space of convergent sequences into real numbers. Makes sense. In there you have some of Z adjoin S, which are the continuous maps from S into the integers, but because the integers have the discrete topology, you can also think of this as a locally constant maps from S into the integers, so they sit inside here. And then if you take the quotient of R by Z, well then you're just taking the quotient on these S value points. You take the convergent sequences from S into the reals, modulo the locally constant functions to Z. Locally constant. And by a simple lemma, you can observe that whenever you have such a map, then local, because the S is covering map as a real to the circle, these are actually the same thing as the continuous maps from S into R mod Z. And so this turns out to be just the same thing as first taking the quotient in topological spaces, and then taking these points. But if you do the other thing of taking the quotient of the reals by the rational numbers, well, then you can, the same recipe works. So you just take the continuous maps from S into the reals, and divide by the locally constant functions from S into the rationals, which is not the same thing at all than continuous maps from S into R mod Q. And so, which would be the maps somehow to this indiscrete space R mod QS. And so this quotient space here, this is really seeing much more of the interesting structures that this quotient still has, because in some sense, when you take this quotient, this quotient still remembers that this R is small. So there you have to take the continuous maps from S into R, so there you can have non-trivial convergent sequences. But what you mod out by, these are just locally constant functions. So this is still the thing as a discrete space. And so in this way, this quotient here as a condensed set, it still sees interesting structures. What's maybe slightly funny about it is that if you ask yourself, if you have a sequence in there and ask where does it converge, that actually can converge to any point. So somehow a convergent sequence is somehow really the data of where everything maps, including the limit points. And in these examples, knowing where all the rest maps may not be enough information. You may map the limit points somewhat to many different points. And this happens in these examples, but that's okay for the formalism. Yeah? There's no axiom that says that where such a convergent sequence should be determined by where all the rest goes. Okay, so yeah, and so yeah, these quotients just exist as condensed sets. And so basic proposition then. And you can, I mean, just as for topological spaces, you can also put other structures on top. So you can consider abelian group objects in topological spaces, so topological abelian groups. Just the same way you can consider abelian group objects in condensed sets and get condensed abelian groups, and you can consider condensed rings and whatnot. So, I mean, all the kinds of algebraic notions that you know and love, you can just put them on top of a condensed set. There's no problem at all. So basically, actually, it becomes even easier because it just means that for any S, this X of S should have the structure. So a condensed abelian group is just the same thing as a functor into abelian groups. So a condensed ring is the same thing as a functor into rings, satisfying those same axioms. And so a very basic nice proposition is that the category of condensed abelian groups this is an abelian category. And it's even one with extremely nice formal properties that I'll probably not want to go into here. Let me maybe just mention that it has has projective generators. So let me maybe also indicate how this resolves this one issue that I talked about, that this can't be true for topological spaces. So I mean, you can still consider R as a natural topology and consider the corresponding condensed abelian group, and you can map this to R with its. You wanted to discrete topology. R is natural topology, and so on S value points. So maps from S. What you get here is the locally constant functions from S into R. These are the maps from S to R with its discrete topology. Well, they inject into the locally constant functions. Into the continuous functions. But the co-kernel, yeah, but there's no trivial code, but not subjective. I mean, they say not any convergent sequence in the reals is eventually constant, of course. And so this means that this map here is actually injective, but not surjective. And so it has a non-trivial quotient, and then you have resolved the paradox. Okay, but this also means we also get something like this L2 space modulo this L1 space is somewhat a condensed R vector space. So for any condensed ring, it also makes sense to talk about condensed modules over this condensed ring. So all these notions make sense. Yeah, so somehow when you do functional analysis now with condensed vector spaces, then you can also consider those funny quotients here. But then actually some weird new phenomena can arise. So here's a proposition. The formula. Taking any sequence of real numbers and mapping it to the sequence xi times log xn, where 0 times log 0 is defined to be 0. So this is a continuous extension of x log x to 0. Defines a non-zero map of condensed star vector spaces from L1 of n to this quotient space. So I mean, this map doesn't look like it should be a map of vector spaces. I mean, I'm telling you that this map is linear. And of course, it is not linear if you don't quotient out by L1, because I mean, this is obviously not linear. But the error term to linearity. So if you somehow apply this to if I call this here f, f of x plus y minus f of x minus f of y, well, is 0, i.e. somehow lies in the L1 of n space. So the error term to linearity of this funny nonlinear map turns out to be somewhat linear. It turns out to be, I mean, be still L1 bounded. And so this means that although you start with this nonlinear map, in this quotient space, it actually becomes a linear map. And so you actually get certain rather weird maps between these condensed star vector spaces. But they exist. Okay. And so this indicates that there is something quite interesting, I think, happening when you really pass from topological vector space to condensed star vector spaces. And so one question that Dustin Clausen and I were back to, was for quite a while. It was fine. So we somehow wanted to redo some of the foundations of functional analysis in this condensed world. And classically, functional analysis is very much based on this notion of complete locally convex real vector space. Okay, so the question was following. Is there a version, a condensed version, you know, that forms an abelian category. So we still want to keep the nice structural or categorical properties that we have in condensed star vector space, and we want to rescue them to this kind of notion of complete forms an abelian category. So if you consider all condensed vector space and just like all topological vector space, it's somewhat too big a category to really analyze. So we want to have some kind of notion of completeness of these objects. So particularly, you want to kind of complete the tensor product of these kinds of condensed vector spaces. And so you need to restrict to a certain subclass. So we want a subclass that we alter for some reason liquid vector spaces. Should be, I mean, this is roughly the same as topological vector spaces. This is roughly the same. This should be roughly the same as the complete locally convex ones. And then there should be also some kind of completion factor. And but we still want that this is an abelian category. But this means that, well, we definitely want Banach spaces to be allowed. Okay, so we would definitely want some of these L1, L2 of n should be liquid. This means that this quotient should be liquid because it should be an abelian category. And this means we get the strange map. And the kernel in particular of this map and because again it should be an abelian category, we have to allow the kernel. The kernel of this funny map from this L1 space to this L2 mod L1 space. And if you think about what this means, it means that you look at sequences where xn times log n, xn is still one bounded. And this guy here is not locally convex anymore. And yeah, this makes life quite a bit more difficult because local convexity, I think, is really used quite a bit in classical functional analysis. So in this Hahn-Banach theorem, but I mean, also for lots of estimates, you somehow want to know that if things are small at 2 points and you can just draw a straight line between them, it will be small in the whole straight line between them. And this just fails in non-locally convex vector spaces. And so we were quite confused about what to do for quite a while until we found a way to do it. And basically the idea is that it's still p-convex for all p less than 1. So there's a notion of p-convex vector spaces for any p between 0 and 1. And turns out that somehow you still stay p-convex for all p less than 1. So this means that, yeah, I mean, let's say that. I want to say this way. If you have some small elements, x1 through xn, then the sum of the ai times xi is small as long as the sum of the ai to the p's is like this way equal to 1. Okay, and so what we proved then is the following theorem. That for any 0 less than p less than or equal to 1, asking for less than p convexity, so p prime convex for all p prime less than p, defines such a notion. Some of p liquid vector spaces inside of all condensed vector spaces with extremely nice categorical properties. And the critical thing is that somehow now it also has a tensor product. So I mean, the definition of a tensor product in functional analysis was one of these. I think Grothendieck defines this back in the day, and it's one of the structures you really want to have, in particular. if you tensor two, I don't know, Frechet spaces, you want a nice Frechet space as a tensor product and so on. And so what turns out is that somehow in this class of p-liquid ones, this still contains all your Frechet spaces. It all contains all these Banach spaces still. And at least if you can restrict to nuclear Frechet spaces, then you have the correct tensor product here. So the tensor product of two nuclear Frechet spaces in our sense will again be a nuclear Frechet space, and will be the usual tensor product of nuclear Frechet spaces. So when we only discussed tensor products, you didn't actually define just one tensor product, but many of them. But you also observe that once you restrict to nuclear spaces, then the difference between all these different choices for the tensor products goes away. And so, yeah, only here you really have this kind of one unique tensor product. And it turns out that in this setting, it also coincides with the tensor product that we define. And because most of the spaces that somehow arise, I don't know, in complex analysis or some smooth manifolds, something like this, you always run to nuclear Frechet spaces, like the space of all multi-functions or space of smooth functions and so on. They're always nuclear Frechet spaces. And so in some sense, it's good enough to really accommodate these here. Okay. And in the last, I don't know, 8 minutes or so, let me say a few words about the proof, because there's something I think quite strange happening in the proof. So, about the proof. I mean, Dustin Clausen and I, we are both number theorists. So maybe it's just because we are both number theorists, but the proof actually uses arithmetic. So it proves a variant for a ring of arithmetic Laurent series. So you fix some real number r between 0 and 1. And then you consider those arithmetic Laurent series a n times t to the n that converge on the disk. Converging this of radius r and actually slightly beyond that. And this suggests onto the reals via sending, I don't know, t to, I don't know, a tenth. If I assume that it's actually larger than a tenth. And so this is some kind of, what we're doing here is we're representing real numbers somehow by decimal expansions. Right? I mean, if this is 1 over 10 to the n, then yeah, these are, you can think of these elements here as some decimal expansions of real numbers. And we really have to go back to someone thinking about real numbers in terms of, say, decimal expansions or binary expansions, or what you, I mean, the base doesn't matter. And we first prove a theorem and then some analogous result for the liquid modules over this funny Laurent series ring. And then deduce it over the reals by a rather simple argument. But a couple of steps in the proof really crucially use that one works in this arithmetic setting. So the first thing is that condensed sets, they are very much based on these totally disconnected spaces. These profinite sets, so convergent sequences, they're always totally disconnected. And this actually means that when you try to prove this foundational theorem about liquid object spaces, then you're actually forced to somehow resolve are vector spaces by totally disconnected sets in some sense. Yeah, I mean, the whole formalism is based on totally disconnected sets, but the real numbers, they're not totally disconnected at all, they are connected. And so there seems to be a complete mismatch here between this condensed formalism and the usual kind of real numbers. And it wasn't clear to us for a very long time whether one could overcome this mismatch. And but eventually we succeeded. And really one key step here is exactly this replacement of the real numbers by this arithmetic Laurent series, because this thing here is totally disconnected. And somehow an arithmetic Laurent series is just determined by what all the coefficients are, but all the coefficients, they just live in discrete sets, they just live in the integers. So this thing is naturally totally disconnected. And so if you work here, this mismatch goes away. But you can still recover the result you wanted by passing through this quotient in the end. And so, but then the argument was still really subtle. I mean, it really mixes kind of rather complicated kind of categorical homological algebra arguments and rather complicated actual hard estimates that you have to do. So somehow you have to control, I mean, there are these kinds of strange maps here, and sometimes you have to get a control on how strange these could ever be. So you have to do some estimates somewhere, but also some kind of hard homological algebra. And I wasn't sure whether I wasn't making a stupid mistake somewhere. And so I actually made a challenge to the computer formalization community. And they answered the challenge. And within half a year, I really formally verified the key argument here. So there's this liquid tensor experiment. Led by Johan Kommelin. They were able to formally verify the key argument, which I was really impressed by. It was a lot of fun discussing with them. I mean, yeah. Anyway. Okay, so this was a comment about the proof, and now I have 2 minutes left. And in those 2 minutes, I just want to say that so there exists more generally this notion of what we termed an analytic ring. So this is a notion of a condensed ring, so something like a topological ring, plus a notion of completeness for condensed modules. So this is, for example, R with a p-liquid structure. And from this, you can build some kind of, take some kind of spectrum and build some notion of, I mean, you can somehow formally repeat what you do in algebraic geometry. So in algebraic geometry, you start with abstract commutative rings without any topology. And then you take their spectrum, and then you get what's called an affine scheme, and then you close those and get schemes, which is this notion that Grothendieck introduced. But in this setting, you can't really do any interesting analysis. You don't have complex analytic spaces in this setting, and so on. On the other hand, people develop all sorts of kind of analytic spaces. So there are these complex analytic spaces. There are also these p-adic analytic spaces introduced by Tate, and then developed by, in particular, by Berkovich and Huber. But some of these developments, they didn't really fit together, and they usually always come with some finiteness hypotheses that things are maybe Noetherian or something like this, which were long dispensed with in algebraic geometry. But using this kind of notion here, it's really possible to develop a very, very general notion of analytic spaces, as general as schemes, but incorporating, so there's this very general notion of analytic spaces. And inside there, you have your good old schemes. You also have what's called formal schemes, periodic spaces, adic spaces more generally. But you also you can also embed complex analytic spaces. But I mean, you don't have to stop there. You can also consider real analytic things, or smooth, or topological manifolds. They can all be embedded into this category of analytic space, and then in some sense they can even talk to each other. And yeah, so that's something the direction I really want to go into, develop this kind of very general notion of analytic geometry based on this notion of analytic spaces. And really, the way to really get all of this started, is really to prove this hard theorem about this new foundation for functional analysis over the real numbers. Okay, and I think my time's up, so let me stop here.
Right. Okay. So, okay. So thank you for the talk. Very good talk. Vielen Dank für den Vortrag, bitte. Right. Since I think there are no questions, neither in the chat nor in the questions and answers, I'll have to do my part. Okay. Right. So I guess one thing that people might have been thinking about when they saw the talk, which was sort of my initial reaction back in one. Okay. So there's a question by Consultable right now.
Okay, I don't see it, so I think you.
Yeah, I'll just read it to you. Yeah. Does the theory of condensed mathematics enable a common definition of Archimedean, non-Archimedean factors of L functions of algebraic varieties?
I don't know so far. I mean, the Archimedean L factors are very much based on Hodge theory, and how Hodge theory fits into this framework is something I really want to think about, but I haven't really started yet. So I do hope that this formalism can help in some way with or reinterpret Hodge theory.
Okay.
So certainly all the ideas they very much come from periodic Hodge theory, and maybe this is related. Anyways, one can hope, but I mean, so far no.
It's yeah, I guess you even have a sort of real version of the Fontaine ring, which is.
Well, I mean, so far there's not a real version of this Fontaine ring.
Yeah.
I'm hoping that there must be something, I believe, but I have no idea what it looks like. Oh, there's this twist door. Anyways.
Yeah, sure. Right. Okay. So the type of question that I was going to ask was, well, so I've seen how this material has shown up in the geometrization of Langland's program, more recently with Fag, and helped out to set up a formalism of some type of sheaves, which was helpful in that setting. But I was wondering, what type of applications do you have in mind for the theory? For instance, would there be any questions or problems, or open problems, I guess, in functional analysis that you believe you can?
Well, the thing is that I don't know anything about functional analysis, so right, I don't know what their open problems are. But actually, I've recently come in contact with a couple of these people from Spain. I think there's some kind of Banach school in Spain at the University of Extremadura. Jesus Castillo, Felix Sanchez, I don't know.
That's great. Okay.
And I mean, they're currently setting up some kind of foundations for also doing cohomological algebra with some kind of Banach spaces. And they've also come to the conclusion that it's best to work with would somehow go into this non-locally convex setting to allow P bar not when P is less than 1. And so there's some key theorem that we need to prove to set up this liquid formalism, that certain X group vanish. And this has a similar consequence in their formalism, that certain X groups vanish. And this seems to be a result they didn't know. And they're currently trying to understand this material.
Right. Okay.
I mean, why do I care about this stuff? I mean, somehow in my work on p-adic geometry, it's really analytic in some sense. I mean, p-adic analytic, which is some kind of algebraic analytic. And I mean, in the future, I hope that there's some way to do what we've done over the p-adic numbers, also like over number fields, hopefully, and then also, I mean, by necessity, also of the real numbers. But for this, we need some common language to talk about all of these things. And so far, I didn't really see any possible language for doing this. And but now this gives really a language where it might conceivably be the case that the kinds of object one has to look at could live in this world. I still have no idea what they are, and I don't really know where exactly to look, but at least it's a formalism in which there's enough space for them to exist.
Okay. I'm not sure if we still have a lot of time left. I think not. I could still ask another question, I suppose. Right, there are no questions in the chat. So, yeah, I think, maybe it's sort of best if we close right now. Oh, there's a new one. If condensed sets can be regarded as geometric morphisms into a quotantic topos.
Yes, I mean, they just form a quotantic topos. Yeah? I mean, by definition, they are the sheaves on some side, except for some stupid set theoretic nonsense that I glossed over completely. And that, I don't know. I mean, yeah, let's just say they form a quotantic topos. I mean, I'm not sure in which sense they should form geometric morphisms. I mean, I guess you can always take a slice topos if you have one, and then. I don't know.
Right. Okay. Right. So now, I guess we should thank Peter Scholze again for his talk. I'd like to remind everyone that there will be some parallel sections starting right now. Yeah. Thank you.
Yeah, thanks again for the invitation and for the introduction. Yeah. Bye.